Hello everyone, today I'll be presenting our results and findings from our project. First, I just want to introduce or talk briefly about the working environment. We use like Google Colab since it provides like powerful GPUs that we can utilize and that are way better than our low-end computers. Because of that, we have like this constraint of only be able to use like the data loaded from the classes, uh, and so we couldn't like upload it because like the only way that Google Colab can connect with is your Google Drive. So you have to upload all the data on Google Drive if you want to use it in Google Colab, and it takes a lot of time. So this is the first thing that I want to make clear, and also because like in Google Colab there are a lot of testing and tries that we did, so I'm gonna just spare you the details and go directly to the tree architecture that we did. So first I want to talk about like the VGG style architecture, which leverage like separable. Here is the architecture. It leverages like separable convolution layers as its core building blocks. So basically, these layers decompose standard convolution into two: one deep depth-wise and one point-wise convolution, which reduce the convolution, which reduce like dramatically like the computational overhead. Of course, it reduces sometimes like the accuracy and the performance, but if you go back to the report, you can clearly see that it was like the fastest architecture in terms of computational power, and also it features like three main block with progressive filters doubling, and then quadrupling, and then quadrupling. Yeah, you can see in here number of filters. It started doubling and then quadrupling, and we started by 128 in numbers of filters. Also integrated like the batch normalization and the dropout layers, since it has shown that the dropout layers provides like more stability and performance, and also like the batch normalization avoids overfitting, and we can see the results. Also, one more thing that I want to clarify: we didn't use it in other architecture, but we used this in here, which is the early stopping. It's basically when an early stopping, which has also a hyperparameter, which is the patience of 5 epoch to avoid like over training. And basically, what it does, like when it sees that the model starts conversion and starts overfitting, it stops it with this parameter of 5 epoch. So basically, if we had like a band, if we can call it like a bandwidth of 5 epoch, where the accuracy has stagnated and also like the model started overfitting, it stops the model before terminating all the epoch, which like increases the the speed of the model. And we can clearly see it in here, like once the validation accuracy started like stagnating, and the training was almost reaching one, the model has been stopped. And we can also see it in the loss, which provide which has been just stopped due to the early stopping, so we can avoid overfitting. And these are the results, and it has shown like a overall performance of 84%. And then moving on to the second architecture, which was it's done which was inspired by the ResNet architecture with the residual block. So basically, it skips connection within its residual blocks to improve we have created the residual blocks in here. It improves the gradient flow and address like the vanishing gradient problem. So basically, it employs like regular convolution layers with progressively downsamples features that maps through strided convolutions. Uh, so basically, it is also organized into three layers with increasing number of filters that keeps doubling and then quadrupling, with also like a batch normalization to avoid like overfitting. And also one more thing, we opted for a real convolutional function for most of the layers. And here is the residual blocks that we can see at the end of each block. And also we use like at the end the global average pooling for this architecture. and a dropout layers, as you can see at the end. And also we didn't use any early stopping in here because we just wanted to see if the performance would really increase or even the computational time would decrease or not. And at the end we had like an overall accuracy of 86%. And if you can see in here, since there hasn't been any early stopping, like the model started like conversion rapidly. But if we had early stopping, we could have stopped like before continuing those epoch, because we can clearly see that they have been like kind of useless since the model already reached or converged toward this value of 86% accuracy. And then moving to the last architecture, which is basically our regular convolutional network, but with a deep number of layers. Basically, we opted for 3 convolutional blocks and 10 connected layers. And in each block, we had like a number of filters that keeps increasing, like doubling and then quadrupling, which with the batch normalization and the dropout layers, and using the activation function ReLU. And of course, we tried with different numbers of filters, but in here, this is like it was like the most performance one with a fixed number of filters, which is 64 across all the layers. And we had in here, if you can see it. Also, we didn't use any early stopping for that one. We had like the best performing architecture with 87%. And also for the other architecture where we tried different hyperparameters, it has been yeah, it's here. Basically, this is like the just the model. This is just like a mockup, and we kept like changing those hyperparameters, and especially the epoch, batch size, and number of filters. We didn't touch much at the learning rate. I guess we've changed it twice or once, and you can see the details in the appendix in the report. So basically, it's a regular convolution network with only like 2 convolutional block and then connected layers which flatten every 10 and create like the layer of the 10 output. And it was like pretty much good, but as you know, the more hyperparameter we have, the more it's hard like to try all the different possibilities, or even like just a bunch of them, since it grows like exponentially with the increase of hyperparameters. And that's it for our video, and you can have like the results in the appendix of the report.